Can you use other fluids? Yes. Which brings us up to the organic Rankine cycle. So what's organic mean? Basically, they use a fluid which is an organic fluid, a high molecular mass fluid. And you want to pick it such that it has the right phase change, at what temperature it boils at or condenses at, pressure it boils at or condenses at. And there's just a whole host of quote-unquote organic fluids that are used or being explored to be used in Rankine vapor power cycles. A lot of times they're motivated by, you got a low temperature heat source. Maybe it's the sun and it doesn't have as high a temperature as in a solar collector as it could be for, let's say, burning coal. It can get very hot. Or geothermal well, which has warm, hot water, but it's not as hot as a coal-fired power plant could make the water. Or you're burning some industrial waste or agricultural waste, or even garbage from a community. And those used to be more popular. They're less popular because of emissions. Because people throw everything in the trash, and it may have a little lead, and a little mercury, a little toxics here and there. And that eventually, if you're going to burn it, it's going to go somewhere. So they don't like it, the emissions from garbage, burning garbage. But there have been a number of plants built that burn garbage and then make electricity. And then biofuels, something specifically grown for a fuel. And why? Because it's carbon neutral. It doesn't count against you in the production, so it's very green. You'll see more biofuels, things grown just simply to burn. Let's take a look at this refrigerant. It's refrigerant R11. It's on a temperature-entropy diagram. The x-axis entropy, you look at the units, yeah, they have the right units. They really don't mean much, a value of 1 to a value of 2, but you can see it's a range of entropy and increasing entropy. You look at the units of temperature, degrees C, from 0 C, pretty cold, to 250 C, pretty warm, okay? So it has a range of temperature. Now, they show a dome. Can you see the dome? What is this dome? Is that the two-phase region? What's at the top of the dome? Critical point. And then they show lines of constant pressure. What about this line? It's 100 kPa, and it comes down and cuts across in the dome, right? This dome is a little more skewed. The water is a little more symmetric. There's 1,000 kPa. That's 100. This is 3,000, 1,000, and 10,000 kilopascal. All right. What I did was I said, well, let's just put a very simple Rankine cycle using this fluid. And so one will be coming out of the boiler, and let's say that your fuel source allows you to go up to 125 C, but not higher. It's your max. So here's 150. There's about 125. You draw a line across. There you go. Somewhere that's coming out of the boiler, it can't come any higher than 125. And you want to expand it such that you get a lot of work out. You could bring it out here, out here, out here, out here, out here, but you're going to expand it to the condenser pressure, true? What temperature are we going to be able to reject heat at? 25 C. Let's pick 25 C. So here's 25 C right there. I have to go between those two lines, okay? Most of the heat that's rejected will be going from saturated vapor to saturated liquid in the condenser, condensing in the condenser, right? So, where do I want to put state 1? What comes out? If I put state 1 right here, that's traditional, that's saturated vapor. If I then expand it through the turbine, isentropic, I'm going to do an ideal Rankine cycle, where do you think state 2 would be? Straight down, and that's where I picked it. So I picked state 1 to be a quality of 100%. All of this data and this plot is generated with NIST software called RefProp, R-E-F-P-R-O-P. I have a number of videos out there. It shows you how to download it, install it on your own computer, and play with it. Free for students if you have about a couple $100. I think it's less than $500. You can buy the professional version. Okay, it's used out there in the industry to evaluate properties. Okay, so so there's state 2, and look at the quality at state 2. 99%. Looks pretty good. Looks pretty good. And then we run over here to state 3. It's going to come out at 25 degrees C. It's going to be completely condensed, right? And then where's state 4? Well, it's 25 plus a half a degree, 25.474 degrees C. The entropy is the same. You went through a perfect pump, and there's state 4 right there. True? So there's the cycle. What would happen if I brought it out to this point? There's state 1. Let me ask the first clicker question. Where would be state 2 on this diagram? Where is state 2 if actually state 1 is right here? Is it in the vicinity of A, this place, B, right on this line, kind of, well, close to that line. Okay, not right on the line, but close to that line. C, below that line, or D, at that line? Where would state 2 be? All right, we're going to go ahead and stop. And we'll show the results. Do you think they'll all be piled up in one location or spread out? Spread out. All right, so we have nobody went for A, which is good. A lot of people went for B. Some people went for C, and then 25% of the class went for D. Let me ask you this question. I'm going to tell you the right answer first. It was B. All right, now, let me ask you this question. At anywhere along this line, what is the pressure? About 100 kilopascal. Okay. A skosh below that line, another line right there. Let's say that one is 90-ish. You see that? It would be a line of 90. How about a line of 106? What does a line of constant pressure 106 kilopascal look like? Right like that, right? Okay. What happens to all these lines when they hit the dome? They go straight across, true? Okay. What would happen if I came all the way down here? Can you tell me the pressure, roughly, of that line? I know is the pressure, if it was actually down to this point right here where it was 25 degrees C and this value of S, right? What would the pressure be? Would the pressure be greater than 100 kilopascal or less than 100 kilopascal? Just verbally. It would be less. Okay, now we're going to start to condense. What's going to happen to the pressure if I went that way? It'd have to go up. It's a constant pressure condenser. So anytime it would be 1 to 2, and 2 would be at the pressure where you're going to have the saturation corresponding to 25 degrees C saturation temperature. So Psat in the condenser, where T in the condenser is 25 C, the majority of heat that you're ejecting, it'll be at 106 kPa. Make sense? So sometimes it really doesn't help to really superheat it, does it? I mean, think about this. I superheat it way out to here, right? Because my temperature is maxed out at 125. Well, really what's happening is it's going lower pressure. That doesn't make any sense, right? If I start moving state 1 out to here, out to here, out to here, that doesn't make any sense at all, okay? All right. Here's the same plot, the same data in a table, but I have asked this question, so we'll start the next question. It says, what is the turbine specific work, lowercase w sub t? Is it 42 kilojoules per kilogram, 47, 52, 57, or 62? One of those is close enough. So don't call it out. Let's do it with the clickers. tell me what is the turbine specific work. These data and the numbering is all the same for the temperature, the pressure, the density, the enthalpy, the entropy, and the quality. Let's go ahead and stop. And we show the results. B it is. Wow, that's great. How did people get the answer B? H1 minus H2, right? And so you look at H1, it's around 448. This one's around 400. Hey, it's around 48. Oh, close enough to 47, right? Okay, very good. Would you like another one of those? Here's another one. What is the condenser heat transfer? For this problem, with that data, what's Q sub C? It's out of the heat transfer out of the condenser. Is it 180, 195, 210, 225, or 240? Stop. Show the results. Wow, that's pretty nice. How'd you guys do it? Hard math. There you go. So it was the difference between 400 and 220. It went down. Enthalpy went down. True? Right. Would you like another one? Yes. All right. What is the thermal efficiency? 10, 20, 30, 40, or 50%? So let's see where everybody was. Very good. 77%. Did that good? Here are the numbers for that problem. So it was 20% efficiency. What's the backwork ratio? Do you want a high or a low backwork ratio? You want a low, but you want a high thermal efficiency. Why did I calculate work net and Q net? Because what's good for the goose is good for the gander, whatever that phrase is. It's like, if I recommend that you do it and I tell you I do it when I solve thermodynamic problems, guess what I do? I do it same. So I wanted to make sure I didn't have an error. So I calculated the work net and the Q net. And then here are all the works, the heat transfer, the work of the pump, the heat transfer in the boiler. That's not the only refrigerant that you could use that's organic fluid. Organic Rankine cycle. You could use also isopentane. Okay, it's a new novel thing. It's like pentane, but it's a working fluid. What do you notice about the TS diagram, the temperature entropy diagram for isopentane? It's very skewed. Shifts way over. It's not symmetric, is it? And so, okay, well, we have 125 degrees C fluid that I can heat it up to, come out of my steam generator. Where do you think I probably want to stop taking it out at? Do you think it helps to superheat but only have it at 125? No, that's not going to help, is it? So we stopped. That was one of the points of that last discussion. There's no sense because your boiler pressure goes down. So bring it out saturated vapor at 125 degrees C. Okay. Now I'm going to expand it, but I'm going to do most of my heat rejection at 25 degrees C. The boiler or the condenser is going to be able to reject heat to something that's 25 degrees C. So I take a look at it. It's going to be like 92 kilopascal is going to be the condenser pressure. See how I got that 92 kilopascal for 25 degrees C, and it's here. So when I expand, can I get this all the way down to 25 degrees C and 92 kilopascal? No, I can't do that. I mean, first of all, the 92 kilopascal kicks up like this. So guess where we end at state 2? I have to go to the condenser pressure, and it has to be isentropic expansion. So there's state 2. And so it's at 92 kilopascal. It's slightly superheated. See that? Superheated at state 2. Okay. Now, once I do that, the cooling right here is just cooling without condensing at constant pressure in the condenser. And then I finally start to get phase change, okay, as I condense it in the condenser. Where is state 3? Where is state 4? Right? So there you go. Look at the numbers here. Well, we'll compare them in a minute, but you can calculate the work of the turbine, the heat transfer in the condenser, the work of the pump, the heat transfer in the boiler, etc. But a big thing is because of the skewed temperature entropy diagram, it's superheated at state 2. Now, this amount of heat rejection right here, okay, is really pretty wasteful, isn't it? Bonus question here, not clicker, but what could you do that would be useful? You could try to heat up that feed water at least that little bit. A little bit, right? Wouldn't that help improve the efficiency of the cycle? It'd be extra piping and extra this and extra calcs, but hey, it may be helpful. So there's a potential use for that. Let's take a look at another refrigerant. This is refrigerant 22. Okay? It was in all of the residential air conditioners in your homes for many, many years. But now if you go buy a brand new unit, they're not going to put in one using R22. It's going to be 410A. That's the common one that's out there. But if you have one that's over 5, 6 years old, it could still be R22. Okay? 10 years old for sure. All right, so what do you notice about the temperature entropy diagram? Very symmetric. So let's say I still have 125 degrees C. That's my heat source. I still have to reject at 25 degrees C, right? Okay, where do I want to bring it out? Saturated vapor at 125 degrees C? Does that even exist on this diagram? Can I have saturated vapor at 125 degrees C? No. So what do we call all this? First of all, this is very high pressure, isn't it? This is 600 kPa, and the 100 kPa is down here. Okay, I didn't even plot it. Okay, the saturation temperature is below 0 degrees C for R22. It's a good refrigerant. It's a good refrigerant, okay? But here we're using it for a vapor power cycle where we have a heat source and we have to reject heat at 25 degrees C. All right. So this point right here, I forgot the name of it. What is that point on the dome called? Supercritical fluid. Okay? That would be kind of up in this region. All up in here, supercritical fluid. Is there a nice, clean, demarcation between that supercritical region and superheated region? No. But it's somewhere like that. You have higher pressure, high temperature. Up in this region is supercritical fluid, right? So basically, you're going to be bringing out a supercritical fluid. Okay, where do you want to stop? Do you want to stop? Let me ask this clicker question. Somebody say, stop here, stop here, stop here, stop here, or stop. Oh, that's too many. Forget it. We're just those 4 choices. Where would you stop? So a lot of people say, stop at C. Okay. Well, I just realized after I asked the clicker question, can you tell where I stopped? Because what I want to do is I want to have isentropic expansion, constant S expansion, right? And if I really want to get a lot of change in enthalpy and I want to have a practical turbine, I don't want 50% quality. Not good. And I don't, out here, I would have to be stopping up here at a higher temperature for the exit. Not good. So C is the best answer, isn't it? And if you look at it, we have this 1.717 for the entropy for both state 1 and for state 2. All right? But notice that the temperature at state 2 is 25 C, so we're bringing it right in that vicinity. But look at that pressure. 1,044 kilopascal for the condenser pressure. The boiler pressure was 5,000 kilopascal, right? And then you have a 1,000 kilopascal condenser pressure. I like to ask questions like this. Somehow there's a pinhole leak somebody took an ice pick, and they went to the condenser, and they went pop, and they popped a hole in the condenser. Clicker question here. You have choice A or choice B. If somebody punches a hole with the ice pick in the condenser, will refrigerant 22 rush out, or will the outside air rush in? All right, so everybody's in. Let's go ahead and stop. I want 100%. Okay, well, we blame it on thick thumbs. You intended A. I know you intended A. But take a look at this pressure. Okay, this pressure right here. Isn't that the condenser pressure? What is atmospheric pressure? About 100 kilopascal, right? Which is higher, 1,000 or 100? It's always going to flow from high pressure to low. All right. Let me do this. I have this problem and I have a condenser. I take a pick and I poke a hole in the condenser. Will the isopentane, the refrigerant, rush out, or will the air rush in? I will start. I have a condenser. It's a cycle. It's running with isopentane. I take a pick. I poke a hole in that condenser. So let's go ahead. Are we going for 100%? Yes. I think we're going to get 100%. Here goes. Stop. Show. 98. That is definitely a slip of the thumb. That is definitely a slip of the thumb. So I asked this question, what is the pressure in the condenser? Around 92. Is 92 greater than 100 or less than 100? Which way is it going to rush? From 100 toward 92? It's a slight vacuum in that condenser. Professor, is there a vacuum pump to create the vacuum? Nope. You may have needed a vacuum pump to purge the air to charge it with the refrigerant isopentane. It's a refrigerant isopentane. I've got the number. It's 601A or something. It has a refrigerant number just like R11 and R12. But anyway, you got to get the air out, fill only with isopentane, and then run the system. Okay. Thank you for participating. This is a summary of all three. Here is that refrigerant 22, the isopentane, refrigerant 601A. Now the question for you is, which fluid would you pick? Which fluid would you use if you had to design an organic Rankine cycle? And those were the three choices. I will now turn it on. We'll take your pick. It's answer A, answer B, or answer C. You would use R22, isopentane, or R11. Yes? So let's show the results. All right, so the results, a lot of people like C. Why do a lot of people like C? Well, it's got a slightly higher efficiency, but I said you could boost efficiency if you just rerouted. Okay, I'm leaving it on so you can change your answer. We're going to change, everybody's going to change the answer to D, and then I'm going to count everybody right, okay? But go ahead, change your answer to D. We're going to see if that works. Okay, but listen to me while you're changing your answer. What are some positives? What are some positives about this? What do you not like about A? The backwork ratio is 10%. I don't like that. I don't like also lower thermal efficiency, but you know what? That backwork ratio really bothers me. Okay. These two backwork ratios are comparable. But there's one other number. It's right in here. Which one do you like? Higher power generated. Which fluid do you like from a work net point of view? For every kilogram that goes in the loop, you're able to pull out 1 kilojoule of work. For every kilogram per second flow rate going in the loop, you get 1 kilowatt power out. True? So which one do you like from the power per unit mass flow rate perspective, or energy workout per mass flow B, that's a great fluid for that. Now, somebody else is saying to their mind, okay, everybody's getting the D. Thank you very much. Now we'll stop. Stop that. Congratulations. We have 100% correct. Now, somebody else says something about, I don't know these refrigerants, but I'm a little worried that they may leak. Good call. It's just like we talked about water. There's some word called toxic. If it leaks out and you inhale a little bit, you worked with refrigerants. You ever inhale a little whiff of refrigerant?
Gene gas from R12, yeah, it's funky, man.
Yep. So not healthy, but it's what happens. You ever spill it on your skin? You ever had any spray on an eye? You ever seen anybody with our refrigerant sprayed in the eye? I have when I was a young man. The oil, the other stuff. So anyway, I try to make it practical that you need to, as an engineer, I've got 5 seconds here. Material safety data sheet. And then you find all the characteristics. Like this was for the isopentane, and they tell you a little bit more about it, but it's extremely flammable liquid. It's heavy vapor. What do you mean by heavy vapor? If you have a spill in this room, where's it going to go? To the ceiling? And if I bend down to pick something up off the floor and I take a whiff, right? All right. They can have ignition problems and flashback, and then central nervous depressant and anesthetic. So all these things you have to be very careful with because stuff does leak. You say, please never spill it. Yeah, well, it's going to get spilled.